nanohub.org. You can follow along with this presentation using printed slides from the NanoHub. Visit www.nanohub.org and download the PDF file containing the slides for this presentation. Print them out and turn each page when you hear the following sound. Enjoy the show.
All right, so this is lecture 23 on AC response. And let me explain why AC response is interesting. DC is interesting because, of course, the photodiodes and normal diode all the time operates in this region, but it's not really great. I mean, you have to really, in order to use it, you have to do something more. And the thing that people did almost like 100 years ago, a little bit more, 100 years ago, was to use this diode for a radio receiver. You know, this transatlantic Marconi and others. So this transatlantic transmission, that was essentially a diode. That was diode with a big antenna. And that caught the signal. The antenna caught the signal. And the diode demodulated it. It extracted back the signal of the voice signal that you wanted to have beyond a carrier. And I'll show you. So this is for my daughter who's planning to buy this, this is actually a simple radio. I mean, not a radio, but you can see that that's a diode. Do you see that long one? And I will ask you to convince yourself that why this works as a radio, because it looks like it's not even connected. You see, it's one side is open, the other side has a switch. But this is actually, try to convince yourself that this is actually a simple diode. Diode you can see, that transparent small cylindrical region. And that coil is that inductor. That wire acts like an antenna, and then that one, that small bulb-like thing, that's a little speaker. And so you can show that essentially it looks like a small radio, and it will work like a radio. You can buy it. Here, of course, the idea is that you bias your diode at a given voltage, right? With a battery, with your AAA battery, you bias it at a given voltage, and then the small signal that is coming in, that's coming from the air. That's the antenna catching a small signal on the order of maybe a microvolt or so. And as a result, on top of the DC bias, there is this AC signal moving around left and right, top and bottom. And as a result, there is a current flow in this. And we want to know how that works. So essentially, instead of drawing that complicated figure, we'll draw a PN junction. We'll have an applied voltage given as VA, and the small VA, we'll use that as the AC voltage, showing that that's coming from the antenna of your circuit. Now, what I want to show you that when you want to analyze a circuit like this, you can replace the diode with simply a resistor and two capacitors. One is called a junction capacitor and another diffusion capacitor, and I will explain that in a minute. But by the way, and this only depends on the small signal. Where is the applied voltage VA hiding in all this? Well, it will hide in the magnitude of the resistance and capacitance. So you will see the applied voltage VA, how it gets in this magnitude of the current. So for a given bias condition, you will have a set of resistance capacitances. If you change the DC bias, you will have a different set of resistance and capacitances. But once you have a DC bias, then the AC circuit, the AC voltage, will just see a combination of capacitance and resistance. Now, why isn't there any inductor in it? That's the question I'm going to ask you later. So, how do I know the resistance or conductance, the G in blue? How do I do that? Or the series resistance RS? Series resistance comes from, because when you have a high bias, then remember that P and N side has a quasi-Fermi level drop, and as a result, that was the series resistance part. So you will write the equation, and you now know, right, that this equation we have derived, this M can be 1 or 2. If it's in recombination generation, 2. If it is diffusion, only 1. If it's ambipolar, 2 again. So depending on where you have biased your circuit, that will be 1 or 2. Take a log on both sides, and this I don't have to tell you, right, how to rearrange this. Take a log on both sides and differentiate with respect to V. differentiate with respect to V, but differentiate with respect to I. Sorry, that's because I want to get the conductance. If I differentiate with respect to I, do you understand the left hand side? It's a log. So log of x, differentiation 1 over x. So you can see that 1 plus I naught has flipped over, and dA divided by di, that's the first term, and you can see the q and beta has gone to the left hand side. Just a little bit of rearrangement. As a result, you can say that delta VA, that's the applied voltage, small signal applied voltage, and the current, that's my G. Delta VA over delta I has a dimension of a resistance, so 1 over resistance, that I'll call G, and this is only applies for the forward bias, right? That curve applies for the forward bias, so therefore I have written a F sub B. You can see the series resistance, so by just measuring it, you can get the series resistance. You know M, right? You know M, and from DC characteristics, you know I naught. Beta is, what is beta? 1 over kT, right? So that's what the one is. So I actually know all these quantities, so I could calculate G. Reverse bias side, well, if VA is negative, then the first term is gone. So what is the reverse bias resistance? That's the constant that does not depend on voltage, right? So is it generally infinity? Yes. If you do not have any recombination, then indeed it is infinity. Recombination or generation, it's indeed infinity. But if you generally have traps in the junction region, so you always have that extra term. Do you remember Ni divided by 2 tau and then square root of V? Do you remember that? Now, if you take a differentiation of that, you will pick up no derivative from the first term, a derivative from the second term. So from that, you will get a reverse bias conductance, and that's the G on the reverse bias side. No rocket science here, right? This is simple. So we can calculate G, no problem. Forward and reverse bias side. Remember, depending on where you have biased it. Now, what about junction capacitance? The capacitance I have to draw. Now, how do I calculate capacitance? The way to calculate capacitance would be that I have biased it. Do you see the Fermi level split? I have biased it in the forward bias side, right? Forward bias side. And then I am showing you that little arrows up and down indicating my AC bias is sometimes making the total forward bias a little bit more and sometimes a little bit less. So it's jumping up and down, smoothly moving up and down. So that's what I'm saying. When it moves up a little bit more current flows. When it moves down a little less current flows. So you can see that there will be an oscillation in the current in the DC case. But similarly, what's going to happen, that the depletion region is also going to modulate little bit, right? Because your forward bias a little bit more or a little bit less is going to modulate, and therefore what's going to happen, if you just look at this junction region, you will see sometimes a little bit positive charge moving up and then a little bit negative charge moving up, right? And these are all majority carriers, because majority carriers can respond very quickly. Holes will be coming from the right hand contact into the junction, and similarly electron will be coming from the left hand contact into the junction, and next to the junction you will see very rapid change in the charges. And this charge, this extra charge, if you just focus on the extra charge, you will see when the bias is a little bit more, then you have charge in one side, this extra charge, and when the bias is a little bit less, then you see from the equilibrium position, the charge will be a little bit less. So you can see the charges will be flipping back and forth next at the end of the junction. But this is exactly what happens in a capacitor. In a capacitor separated by an insulator, not semiconductor, an insulator, when you apply a AC bias, charges dance around these two electrodes, right? Go up and down in magnitude, same thing is happening. So therefore, this is a majority carrier effect. This is very important to understand. Minority carriers couldn't do it, and I will explain in a second. But the majority carriers can do this, and if it can do so, you can easily calculate what the capacitance is. You have done this many times, right? Epsilon A over D. D is the distance of the charge separation, and that's Wn over Wp. You put that formula back in, and you are actually done. Do you see why the capacitance, junction capacitance should depend on where you are operating the device? Look at the VA on the numerator. So the numerator contains the applied bias, and that you can help you to define the junction capacitance at that bias point. Okay, so this is not difficult. If you measure it as a function of VA, it goes as 1 over VA, right? This is in the denominator, square root of 1 over VA. So therefore, the red line essentially will look like this as a function of VA. Now, as you increase the voltage, the capacitance goes down. Is that right? Because it's 1 over VA. And so you can see the red line, the more negative bias you apply, the red line is gradually getting smaller down the road. Now, this is the first time, remember, then we'll be able to measure VA. As one thing I have mentioned about this course, that every time you see a theory, you must ensure that you understand how this is measured. If you didn't understand it, then it's not good enough. I told you about how to calculate VBI before, built-in voltage. I did not tell you how to measure it, because how do you know your theory is correct, So the only way is to measure it, and you can easily measure it in this way. The capacitance you can measure, and then if you plot it in a particular way, and the particular way is 1 over Cj squared, square of the capacitance, then you realize that this becomes a straight line. And the point of intercept in the x-axis, right, that is VBI. And from that, you can calculate back what the VBI is. You see it's a straight line, and that's on the right-hand side. So you can calculate from here, the right-hand intercept point, what the VBI is. Now, this one also allows you to do variable doping. If your junction doesn't have a fixed doping, remember what this does is that it separates the charges, plus and minus charges, at a certain distance. And it only probes the doping at that point, the amount of plus and minus charge. So if you deplete it a little bit more, and it goes to a separate place where the charge is a little bit different, then this capacitance formula will pick it up, because NdX is the doping at the point of the junction, end of the junction. So again, you can do the same formulation, and from the local derivative, and this I will ask you to verify, from the local derivative of 1 over Cj squared and a VA curve, this one is always, the intercept is always QVBI. But from the local derivative, you can pick out how the doping is actually changing across the substrate. And so this is a very interesting one, but take a look when you have a few moments. Now, one thing that is sort of important to understand, that when you modulate the charge on the left-hand side, why is it that it immediately comes to the junction? Why doesn't it take a huge amount of time? When you turn on a switch for the light, why is it that light immediately lights up? The electrons don't sort of walk around and then say, okay, wake up everybody, and then tries to, turn on the light. That's a very important thing, and that's why in these circuits or models, in the majority carrier side, there is no capacitor or inductor to represent the majority carrier side, just the resistor, Rs. And this you need to understand, because that is called a dielectric relaxation time. In the majority carrier side, why there is no capacitance or inductance? In the majority carrier side, I only have drift current. Is that right? Because that's most of the electrons are over there. And let me assume no recombination and generation. But I'm looking at a transient that I'm oscillating on the left-hand side, and try to see how long will it take for the signal to propagate to the junction. That's what I'm trying to answer. Okay, so that equation I already know. Now, do you agree with these statements? Because I'm doing dN dt, only the excess delta n is what I need to focus for. And for the current, I only have the drift current, so I have put it in. And therefore, I can get an expression for dE dx, so that delta n dt is proportional to dE dx. Nothing complicated, I haven't done anything. Now, from Poisson equation, I also know dE dx But do you realize why I have dropped all these terms, Na and P? Because it's the N side. I better not have any Na. So I also dropped P, and as a result, Nd is almost equal to N naught also, right? It's a majority carrier side. And so what I will have is Q delta N divided by epsilon. I put it in the second equation back in d dx expression, and I get an expression for delta N delta T. Now this one you can solve, can you? This is a first order equation and you can solve, and this is the solution. This says that if you start a oscillation on the left hand side, how long does it take for that oscillation to essentially get out of this material, right, to the outside of the junction, because this is how fast the whole perturbation decays as a function of time. Now, if you calculate how long it takes, that's 1 picosecond. Within a picosecond, or a fraction of a picosecond, from one side of the signal, it comes to the other side. That's why when you turn on the light, this light immediately turns your bulbs on. You don't really have to wait, because here the electrons are not going themselves. One electron is saying to the next, its neighbor, that move. The next electron is saying to the next, that move. And so this cascading process goes on without an electron physically have to move all the way. And that's why this process is so fast, and there is no capacitance or inductors in this series resistance part of it. It's very important that you understand this. And you will see it in many, many different contexts in other years. Now the next one is the minority carrier diffusion equation. Junction capacitance is only for the majority carriers. Minority carriers cannot respond this fast, right? Because minority carriers go by diffusion. Diffusion cannot propagate the signal as fast. In diffusion, electrons really have to move on their own. No help from, no group effort here. Now diffusion capacitance, how will you do that? Let's say I have biased a signal, a biased diode. So I have that triangular profile, no recombination. Now I am forward biasing and a little bit with this small voltage from my antenna. As a result, what's going to happen? That there will be a modulation of the corresponding carrier concentration. Why is it like this? Because it's like a rope or a string on which one side you oscillate, and you can see that as you oscillate, depending on the frequency, there will be a wave going to the other side. At low frequency, there will be a single wave. As the frequency goes up, you are pushing the electrons to go this way. Before they have chance to get out from the other side, you have reversed your bias and say, come back. And so they cannot decide to go or come back, and therefore there is this periodic oscillation going down the road. If the frequency is high, then the oscillation will also go up, right? So that's what I'm saying. If it's close to DC, it will almost be flat. Okay. Now, the math of it, well, that requires you to wake up now. This requires that I solve this problem correctly. This requires that this is a minority carrier side, and I shouldn't have a drift term, right? Previously, I had a drift term because I was looking at majority carriers. Minority carrier on the right-hand side, the electrons, so I dropped the first term. Now, I put that thing in here, and this becomes this horrendous thing. But let's think about it. The left-hand side is N, dN dt. N has three p's. One is N naught, the equilibrium piece, before I have applied any bias. Does not depend on position, doesn't depend on time. So that's N naught. I have applied a DC bias. Then, of course, it has changed the carrier concentration a little bit. That's my triangle, this magenta triangle. And that's DC depends on position, but doesn't depend on time. Is that right? Because, of course, nothing is moving. And then I have an AC signal, the extra thing is coming in. That one depends on both time, and you can see from this oscillation of the blue curve on the top and right side. It depends on time because it's a wave moving forward, and it depends on position because it's a slope, you can see. So therefore, now you realize what I have to do in order to simplify this equation. The first term, N naught and NDC will go because they are not changing with time. In the second term, only N naught will go because the DC term and AC, they depend on position. So I shouldn't drop those. And then you have the recombination term. That's fine. Of course, the same will happen for the holes. The holes are trying to go this way, but we'll focus on the electrons, and that will probably do it. So you see this, that there is this DC and AC term. Of course, now I should be able to separate, because I should be, if these two equations, two sides, left hand and right hand side, must be equal to each other, then this must be equal to each other for all omega. Any frequency that you come in, it should be equal to each other. And if that is the case, my DC and AC components must separately satisfy this equation. Moreover, so let's take the first derivative. I have dropped the N naught and NDC term, right? Do you see that? And do you see why I have picked up a j omega? Because I have taken a derivative with respect to time. I have picked up a j omega. Do you see on the right hand side that I have dropped the second derivative with respect to position for N naught? I can do that. That's the DC. Of course, other things I cannot drop. Now, I can separate this thing out. Assume that for me, omega is equal to 0. So in that case, only the DC components remain. So you have seen this equation before, right? The DC, second derivative, and delta n over tau. Well, that was my minority carrier equation. I haven't done anything because I haven't applied any AC bias, any antenna signal. So therefore, it should be. And therefore, as a result, you know also the solution in terms of exponential, because now you have a recombination term. What about the AC? The AC is whatever term you had on the top, you just collect them all up. You can see j omega tau n that I have picked up from the right hand side, left hand side, and pulled it up in here. Now do you see, and this is the crucial part, that these two equations are essentially the same. If I redefine tau n divided by this 1 j omega tau n plus 1, if I redefine the whole quantity as if it's a AC lifetime, then these two equations are mathematically exactly the same. Do you see that? As a result, their solution will be exactly the same also, except this Ln, which is square root of dn multiplied by tau n, that changes. But other than that, it's exactly the same equation. Now, if I assume that this minority carrier region is long, then of course you realize that d will go to 0 because it cannot go exponentially up forever. Only the C term will remain. So that's only redefinition here, nothing more than that. Now the boundary condition is something we have to worry about. Why? Do you see why I cannot simply equate? So I want to know what is the value of the excess AC concentration right here, excess AC concentration for the time dependent AC case. Now do you see why I cannot simply equate the two sides, the rate components directly? Because on the right hand side, the j omega t is sitting on 2-story up. It's not only sitting on top of an exponential, it is sitting on another top of another exponential. So therefore, I need to simplify this a little bit before I can equate. So that's the tricky part in this whole business. Now, do you agree that I can write it this way? That the exponential of two terms can be written as this multiplication of the two exponential. That's fine. Now, this AC voltage is minuscule, right? Microvolt. And you have applied a bias of a volt. So it is e to the power x when x is very small. In that case, you can expand it. E to the power x is equal to 1 plus x. And that is what I have done the expansion for. And once you expand it, this time you can equate the j omega t term on both sides because they are on the same level. And then you pick up the AC voltage, extra AC component, which is given by the magnitude of this oscillation. That's given by this. And it depends on the DC voltage, because the more DC voltage you have, then the correspondingly more AC voltage you have. You can see that the VDC term over there. So I'm done actually. I can then, this AC current will be the derivative of the AC extra carrier concentration. And I'm sorry. So this one You already know this solution. You know the value for C. I just derived the value for C. You insert it in that expression, take a derivative, and that gives you the AC current. And the AC current is here. And you can see the VAC, the AC voltage. So if I divide the current by the voltage, what do I get? I get that's something that has a impedance or 1 over the impedance, right? Admittance. And so because it's a AC thing, and that's what, after I simplify, this is what I will get. Now, why did I get this? J omega tau n. Where is this hiding? Ln, exactly. So Ln was where, remember, the tau n was normalized by this factor. So when I wrote it out, the Ln properly, this got me flipped over and got me this extra term, j omega term. And you can see why they say admittance, not simply a resistance, because there is a j omega sitting here. Okay, so one more line and we are done. If I plot these capacitances and conductances that I have done, so that's my admittance. I can separate the real and imaginary part. And if I separate the real and imaginary part, this is the conductance and that's the capacitance. Now you can see when omega is small, do you see what's going to happen when omega is small? In that case, this GD will essentially become a constant. That's fine. What happens when omega is large? Do you agree with this statement? That when omega is large, then it should go as a straight line on a square root of plot or in log-log plot with a slope of half. Why is that? Take a look at that. So if omega is huge, then I can drop the 1 in comparison. I can also drop the other plus 1 in comparison. Now I have a square root inside, that gives me omega tau n. Then I have a square root outside, that gives me another square root. That's why it goes as a square root of omega. What about the capacitance? Do you see this? I can drop, again, once again, omega is so large, I can drop the 1 and a minus 1 I can drop, right? And as a result, what should I get? On the top, in the numerator side, again is square root of omega. But this capacitance is going the other way. Why is that? Because look at the left-hand side, I have a omega sitting on the left-hand side. So when I look at the capacitance, it goes as 1 over omega. And do you see this amazing thing? That the conductance multiplied by the capacitance is essentially frequency independent. Regardless of how quickly you modulate, 100 kilohertz or a megahertz. Let's say you want to hear this AM radio or FM radio. Everybody has a different frequency band, right? Regardless of what you do at all those frequencies, essentially the conductance multiplied by capacitance is independent of frequency, although individually they are dependent. Now physically, I'll end with this. Physically, why is it omega dependent? Because of course you can see that when you have low frequency, the carriers can really go from one side to another. You have a resistance, you don't have as much capacitance. When it's oscillating very fast, the carriers cannot go to the other side. It's saying go and then say it pulls it back. And so there is a phase shift between the voltage you apply and the current which is trying to keep up. And there is that phase shift, frequency dependent phase shift, that is getting reflected in the capacitance, you see. As a result, this has this capacitance dependence. So to conclude then, this small signal response is very important for many analog circuits, small signal, and that was central to this argument. Then these parameters, this capacitance, inductors, and the capacitances and the resistances, they always depend on this DC operating condition. You saw that, right? The conductances has VDC inserted into it. And it's very important that you distinguish between majority and minority carrier effects. If you don't have any minority carrier, no diffusion term. Majority capacitance is always there. But if you don't have a minority carrier transport, there are many devices like your MOSFET, may not be a minority carrier device. In that case, you will not have a diffusion capacitance. So very important to get this various pieces in the right place so that you can apply it into a novel context. Okay, thank you.